Good morning, everyone. I hope you have had now enough time to, go through all the earlier videos carefully and solve the question banks that you have. Now we will again start with the random variable discussion. Let me revise the definition. So, so let me call it definition 1 because today we are going to introduce another definition. This definition 1 is also known as classical definition. So what does the classical definition say? Let x be a function from omega script a to r script b. Okay, omega can be anything. R is a set of real numbers, b is a Boral field. Okay, then we say that x is a random variable with respect to script a, or basically with respect to omega script a, if x inverse of s is in script a for every s in script b. Okay, that is inverse image of a Boral set is in script a. That is our classical definition. Today we are going to introduce another definition which is known as economical definition of a random variable. Okay, so how does the economical definition work? So we start with the same setup. Let x be a function from omega a to rb. We say that x is a random variable with respect to omega script a or with respect to a if x inverse of s is in a for every s in C, where C is a class of sets which can generate Boral sigma field. Okay, for every s in script C, where sigma of script C is script B, means the minimal sigma field generated by class C is the Boral sigma field. So we can take, for example, C as set of all intervals of the type AB, where A is less than B and AB are in R. Okay, in fact we can take any of the 8 types of intervals. We know that in each of these 8 types of intervals, classes of 8 types of intervals generate the Boral sigma field. Okay, and traditionally we use this C. So intervals of the type minus infinity to x, where x is in R. Okay, so traditionally we use this script C. So if we prove that inverse images of sets of these types are in script A, then we don't need to prove for every Boral set. It automatically happens that for every Boral set the inverse image would be in script A. Okay, we won't go into the proof for this, but you should remember the concept. Why the name economical definition? Because we know that Boral sigma field contains many sets, right? Boral sigma field have many sets, and this C is a subclass of Boral sigma field. So C has very few sets compared to entire Boral sigma field, and we are saying now that it is enough to check for inverse images of these sets whether they are in script A, and you don't need to then check for remaining things will automatically be in script A. Okay, so it's reducing your work drastically, hence we are saying that this is an economical definition of random variable. Okay, let me take one example just to make the concept more clear. So consider omega equal to A, B, C, D. Okay, there are 4 letters, and let x of A be defined as 10 and x of B, x of C and x of D, all these be defined as 100. Okay, so x takes only two values, 10 if omega is A, small omega is A, and 100 if small omega is any of B, C and D. Okay. Now let me consider a class of sets, say C be 10. Okay. Now what would be X inverse of C? X inverse of C, now since 10 is coming from A, so X inverse of C would be singleton A. Okay. Now two questions. What is the minimal sigma field generated by C, and what is the minimal sigma field generated by X inverse of C? Remember, X inverse of C is on the left side. Okay, so it is part of omega, whereas C is part of R. Okay, C is a collection of subsets of R and X inverse of C is collection of subsets of omega. So I can construct sigma fields on both sides. So sigma of C would be 10, then complement of 10 would actually be minus infinity to 10 open union 10 to plus infinity. Okay, this is complement of this set 10. Then union of both these is omega. Omega means actually R here. Union is R. Of course, if I have R, I have to have empty set. So this is the sigma field generated by C. Right? 10. Then this R and phi. And what would be sigma field generated by X inverse of C? So it is A. Then complement of A is BCD. Their union is ABCD, that is entire omega, and of course its complement phi. Okay. Now let me take X inverse of this. So X inverse of sigma of C. So I have to collect inverse images of sets in C. So inverse image of 10 is going to be singleton A. Inverse image of entire R, if I consider, it's going to be entire omega. Inverse image of phi is entire phi. Now what remains is inverse image of this thing. Inverse image of this means I have to see which elements are there and I have to take inverse images of them. So see, 10 doesn't belong to this because this is open at 10 and again it starts open at 10. So the only possible value of X that belongs to this set is 100. So inverse image of this set would be basically inverse image of 100, that is B, C, D. Okay. So what are we getting is sigma of X inverse of C is same as X inverse of sigma of C. And in fact this is the reason why we can check only for sets coming from C and then automatically it would be true for all Boral sets, that sort of thing. Okay, this is one example. Now we have to, we'll see a couple more examples, but before that let me introduce another concept. So we need something called as sigma field induced by a random variable. Okay, what do I mean by that? Let me explain. So again, let X be a function from omega script A to R script B, and now I am going to say that X is a random variable. So I suppose automatically know that X is a random variable. Okay, further it is given that X is a random variable. Okay, further it is given that X is a random variable. Okay, so we define X inverse of script B as collection of all those A's in script A such that A is equal to X inverse of S for some S in B. Okay, so we are basically collecting inverse images of all the Boral sets. Now because x is a random variable, we know that x inverse of script B is subset of script A, right? This is because x is already known to be a random variable. And this x inverse of script B would be known as, so x inverse of script B is the sigma field induced by x. Okay, sigma field induced by x. Why? Because it contains only the inverse images of Boral sets under x. It does not have any extra sets. Now you might have one question. What is the guarantee that x inverse of B is a sigma field? Because we haven't made it a sigma field yet. We are just collecting inverse images of sets, inverse images of Boral sets under S. So what is the guarantee that this is a sigma field? So this comes from the earlier result. We have seen that inverse image of a sigma field is a sigma field. Okay, we have seen it in an earlier lecture. Inverse image of a sigma field is a sigma field. Okay, therefore what we know is, because we know that script B is a sigma field, x inverse of B must be a sigma field. Okay, now what is the peculiarity of sigma field induced by random variable? It does not contain any other extra sets. It contains only the inverse images of the Boral sets under that particular random variable. Okay, therefore we can also say that x inverse of B is the smallest sigma field with respect to which x is measurable or x is a random variable. What do I mean by this? If I take some other smaller sigma field, then, so let me take, so this is say omega. We have collection of subsets of omega. So suppose this collection of subsets of omega is actually say x inverse of script B. And now I consider a smaller collection. So I consider only these two sets. Okay. Now if I consider only these two sets, then I know that there are some Boral sets whose inverse images are not included in this smaller thing, because these came in x inverse of B because they were inverse images of some Boral sets. So if I am keeping them out, it means that there are some Boral sets whose inverse images are not in this thing. So x would not be a random variable with respect to this smaller sigma field. Okay. Hence I am saying that x inverse script B is the smallest sigma field with respect to which x is measurable or x is a random variable. Okay, for x to be a random variable, what you need? You need inverse images of all the Boral sets to be in x inverse of script B. So you cannot have a smaller field. Okay, and therefore we can have another notation sigma of x for x inverse of B. It is kind of minimal sigma field generated by x. Okay, it's minimal sigma field generated by x. But please notice the difference between the notations. When I say sigma of script C, I am saying okay, take script C, take all the sets from script C, take their complements and unions and then proceed. Okay, whereas what I am saying now is take all the Boral sets and take their inverse images under x, and then that would be your sigma field. Okay, so sigma field generated by a class of sets and sigma field generated by a random variable, they are two completely different things, even though the notation looks same. Is it okay? So let me take another example. Suppose I have this omega, I have this a1 as one subset of omega, a2 as another subset of omega. Let me define x as say 10 over all these points. So x takes value 10 if x is in if omega is in A1. Then in this remaining part, x takes suppose value minus 10. Okay, in this remaining part of A2, the common part is gone with A1, and then in this further remaining part of omega, that is outside A1 and A2, x is suppose taking value 0. Okay, so you have defined x for every omega, right? Because that is necessary, otherwise x won't be a proper function. So let me write down the notation. So you have omega, and let script a be power set. Okay, so script a be power set of omega. So basically power set contains all possible subsets. So every function would be a random variable on a power set. Okay, and we are defining x of omega as 10 if omega is in A, x of omega is minus 10 if omega is A means A1, x of omega is minus 10 if omega is in this part of A2. Okay, so it is A2 intersected with A1 complement, correct? And x of omega is 0 if omega is in complement of A1 union A2, outside both of them. Okay, so we have to consider inverse images. So we'll divide them into different possible types of sets. We'll divide the Boral sets into different possible types of sets and then consider the inverse images. So we want x inverse of S, where S can be of different types. One simple possibility is x doesn't contain any of these three values. So 0 doesn't belong to S, 10 doesn't belong to S, and minus 10 also doesn't belong to S. Then another option is 0 belongs to S but other two don't. In this way we will actually have 8 possibilities, right? For each of 0, 10 and minus 10 I have either belonging to or not belonging to. So let me first write down those possibilities. It's like, you know, writing down 3 coin tosses. So head means say belong to and tail means doesn't belong to. Okay, 0 doesn't belong to S, 10 belongs to S, and minus 10 also belongs to S. 1, 2, 3, 4, 5, 6, 7 I have done, and the last is everything belongs. Okay, now if only 10 is in S and 0 and minus 10 are not in S, then I get inverse image of S as simply inverse image of 10, that is A1. Okay, so that is A1. If 0 belongs to S, other two don't, then I get inverse image of 0. So inverse image of 0 only is A1 union A2 whole complement. Okay, so this is A1 union A2 whole complement. Then 0 and 10 are in S, but minus 10 is not in S. So I will have A1 union with A1 union A2 whole complement. So A1 union A2 whole complement is the green region, A1 is the blue region. So what I am left with is if I take union of them, what I am left with is the red region. Okay, so complement of red region, and red region is what? This A2 intersection A1 complement. So I need complement of that. So maybe I can keep it as it is. So I will just write as A2 intersection A1 complement whole complement. Okay. Now if 0 belongs and minus 10 belongs but 10 doesn't. So 10 doesn't means 10 is the blue region. So complement of that. So I get A1 complement. From here, so minus 10 belongs and everything else doesn't. So minus 10 belongs means basically I'll just get inverse image of minus 10, that is A2 intersection A1 complement. So I have A2 intersection A1 complement. If only 10 belongs, then I get just A1. Okay, I'm sorry, here I had said nothing belongs, so this has to be an empty set. Okay, this is, this is a mistake. This has to be an empty set. Okay, because here nothing belongs, right? I misread it. Then 0 doesn't belong to S, 10 belongs to S, minus 10 belongs to S. So everything except 0. So 0 was the green region. So everything except that means complement of green region. Green region is A1 union A2 whole complement. So its complement means A1 union A2 and everything belongs is omega. Okay, your job is to check if this is a sigma field. Okay, and another approach is to consider sets of the type minus infinity to x. So you have minus 10, 0, 10. So you will have how many types? One type when x belongs to this part, one type when x belongs to this part, third type when x belongs to this part, and fourth type when x belongs here. And from these four, if you generate a sigma field, it should match with what you have here. Okay, that is also homework. Okay, try to do this. If you can't, then we will discuss in the next lecture. So this is the definition of induced sigma field or sigma field induced by a random variable. Now we have to introduce one more concept, Boral function. What is a Boral function? So we know what's a function. Function is again a mapping between two sets which has certain properties. Properties means it can't be one to many. So you can't have two images for one point. Okay, you can't say that x of omega is a1 as well as a2, that is not allowed. And every x should have some image. Okay, now let G from RB to RB be a function. Okay, let G be a function defined from real numbers to real numbers. Then G is said to be a Boral function. G is said to be a Boral function if for every S in script B, G inverse of S is in script B. Okay, so it's similar to measurability, but because now this is also RB and this is also RB, I am saying inverse image of every set from here should be in here. Okay, G would be a Boral function if inverse image of every Boral set is also a Boral set. So basically we are saying that a function measurable with respect to Boral field would be called as a Boral function. Okay, a function measurable with respect to Boral field would be called as a Boral function. Is it okay? A typical example is, say, gx is equal to x square or gx is equal to e raised to x or gx is equal to log x. These are all examples of Boral functions. Okay. Let us check how they are examples of Boral function. So what we mean is, if we take inverse image of any Boral set, it should again be a Boral set. So let me consider for x square. and we won't do for all Borel sets, we will consider only for intervals, and say intervals of the type minus infinity to x, because we know it is enough to check for those. So what would be inverse image of this interval under x square? So first of all, if x is negative, means if x is here, then the interval consists of only negative numbers. So of course inverse image is going to be an empty set. So G inverse of minus infinity to x would be an empty set if x is negative. So no worries there. Because phi is obviously a Borel set. So phi belongs to script B. Now if x is positive, then what happens? If x is positive, means x is somewhere here, then of course this part still doesn't contribute to inverse images. This part contributes. So what I am left with is inverse images of numbers between 0 to x. So I need inverse images of this, means I need to find out all those y's in R such that y square belongs to the interval minus infinity to plus x. Okay. So what would I be left with is minus root x to plus root x. Right. Inverse image of this interval would be this when x is positive. And we know that since this is an interval, this is also a Borel set. So inverse image of this Borel set is also a Borel set. And these are the only possible categories: x negative, x positive. So inverse image of every Borel set of this type is a Borel set. Hence, we can conclude that inverse image of every Borel set would also be a Borel set. Okay. So this is how you check Borel measurability. I'll stop here today. We'll continue with further properties of Borel functions tomorrow. Thank you.